This week we are making an affordable star tracker. So good afternoon and a warm welcome to the Refreshing Views Observatory. My name is Mark Radici. Now if you've ever wanted to take a picture of the night sky, you need to take a multi-second exposure. The starlight's so faint. Now the problem with that of course is that the stars are ever so slowly rising and then eventually setting, so they're moving across the sky. Now some people deliberately enhance that effect and take wonderful pictures of stars trailing. Now if you want to take pictures showing the glory of the summer Milky Way or the star fields around Orion or the pictures of the moon rising, you need some way for your camera to track the stars as they move across the sky. Now you can buy these trackers for a few £100. Now I wanted to make something that was far more affordable, something I could put together in my home workshop. So we are going to need some plywood, a packet of hinges and the screws that come with them, a 12 volt 1 RPM motor and a switch to turn it on and off, a length of M6 rod and a bag of screws, nuts and bolts, etc. to fasten it all together, and a couple of 40 tooth plastic gears. So this is how the star tracker works. We are outside under a clear sky looking up at this wonderful star field ready to photograph it. Now because it's pouring with rain, I'm actually in the garage pretending I'm outside under a clear sky. I've got the star tracker mounted on the camera tripod, and the first thing I do is sight it on the hinge and make sure that I'm pointing at Polaris. So Polaris is up there lined up with the hinge. I then fine tune the alignment with the small finder scope. I then adjust the camera so that I'm positioning, photographing whatever I want to photograph. Something setting in the western sky in this particular example. It's then a complicated task of turning it on. And this is how it works. So the motor drives the gears push against the threaded rod rotates around the hinge, and the camera then follows the stars. So how do we build this masterpiece? Well, we want the camera to rotate 360 degrees in 24 hours, which works out 0.25 degrees per minute. It's actually a bit less than that, but it's such a small error we don't need to worry about it. So if we use a length of M6 rod, it has a pitch between the threads of 1mm. So if we use a 1 RPM motor, we are actually advancing the rod by 1mm per minute. So if we draw that up into a triangle, split that into a right angle triangle and use some trigonometry, we find the distance from the centre of the hinge to the centre of the rod at 0.25 of a degree with a 1mm height is 229mm. And like a good student, I've shown you my working. So key to this design is curving the threaded rod so that the plywood follows it, bends around the hinge without error. Now I cut a wooden template on some scrap wood on the table saw and then bending it by hand. Then simply look at which part of the rod best follows the arc and then cut out the best part, the best sort of middle third or so. Then cut your plywood to length, and I glue some thin strips of plywood onto the outer edges as well. That makes it a bit stiffer and helps protect the gears. I'm not sure if it's really necessary. Fix the hinges at one end and drill a hole in each piece of plywood 229mm from the centre of the hinges. Mount the motor to the underside and solder on a toggle switch and a connector, and I mounted the motor so it was on a pivot so I can mesh the gears together. Then fix your gears to the motor and attach the other gear onto the threaded rod, and we're away. Then add a T-nut for the tripod plate so that can screw on. Put a 3/8 screw for the ball head so that you can mount the camera. Screw on the finder scope in the corner. It's then a case of waiting for a clear night and looking at the weather we've got at the moment. I can't see when that's going to happen, so I'm really excited to be actually using this and be out under the night sky. So I really want to try out the star tracker and see how it performs under the night sky, but the weather remains truly awful. So I went back into the workshop and added some simple upgrades. I superglued a sighting tube to the hinge to aid lining up on Polaris, and I've glued up a plinth so that the ball head is horizontal for my latitude when I set it up. And I also timed how long it takes for the gear to do 1 revolution. And to my horror, I've noticed it's actually doing 1 revolution in 50 seconds. So not the 1 minute I designed it for, not the 1 minute it's specified for. So I've had to go and buy a 12-volt speed controller. And of course, in true online ordering way, the first speed controller was faulty, so I'm now waiting a replacement. So while I wait for that to arrive, let's just quickly tot up the spend on the project. So the big ticket items just came in at over £30. Now I 3D printed my gears at home, but you can buy plastic gears online for a few pounds or steel gears for a few tens of pounds. So let's put them down for a £5. I've also had various odds and ends in my spares bin, so I've made a guesstimate of what it would cost to use, and the total comes in at less than £50. So not bad, a widefield star tracker for £50. So I actually had some clear skies briefly last evening, just before it got dark. It was still too bright to see Polaris, so I used my compass and digital spirit level on the phone to vaguely polar align, and then track the moon for nearly an hour, taking a picture every 10 seconds. So you can see here we're tracking, but we're going slightly too fast, obviously without the new speed controller, and the polar alignment is off a bit, but it's good enough for government work, as they say. It was a simple case of resetting the gears, ready for another session, if it wasn't cloudy, of course. So a £30 star tracker seems to be working. I'm going to keep my eye on the forecast. Right, stay safe, and if you have a moment, please subscribe, and let me know if you have any questions or comments on the star tracker below.